Hi everyone, I am Lin Fangzheng, a joint PhD student at the University of Birmingham and the Southern University of Science and Technology, under the supervision of Professors Hyungjin Chang, Alice Leonardis, and Wei Zhang. I'm excited to introduce our latest CVPR work, GeoReF, which focuses on category-level object pose refinement. Category-level object pose includes the object's 3D translation, orientation, and 3D size. Accurate object poses are crucial for applications in autonomous driving, robotic manipulation, and augmented reality. In this work, we address the challenge of category-level object pose refinement. Given the point cloud of a target object, an initial estimation, which may not be accurate, and the shape prior, our goal is to estimate the relative pose between the ground truth and the initial pose, ultimately achieving high accuracy object pose estimation. Typically, this refinement involves iteratively comparing the transformed shape prior with the input point cloud. However, due to significant shape variations within a category, the target object and the shape prior often differ in shape and size, making relative pose estimation challenging. Existing algorithms do not effectively address this problem. The key problem is how to address the shape discrepancy between the shape prior and the target object. A natural idea is to leverage deformation. For example, we can apply a deformation module to the shape prior to make it identical to the target object, and then perform pose refinement based on them. This method addresses shape discrepancy but poses a strong requirement on the generalizability of the deformation module, as it needs to handle all unseen shapes during training. Additionally, high-quality deformation in every shape detail is challenging, especially for complex-shaped objects. Moreover, estimating the pose differences between the two shapes may not need every shape detail from them. When we look at the shape differences between them, another idea is to leverage sparse geometric features. For example, we can apply 3D graph convolution on both shapes to extract high-level geometric structural information, and then using the extracted latent geometric features for pose refinement. Even though this method can avoid detailed shape information and the latent features are easy to learn, it still fails to resolve the shape discrepancy problem in sparse geometric structures. So, our idea combines the advantages of both sparse geometric feature extraction and deformation. Specifically, we still use 3D graph convolution to extract sparse geometric features from both shapes. Instead of directly applying these features, we introduce two learnable affine transformation networks to adaptively align the geometric structures and their corresponding features, allowing the neural network to better recognize the relative pose between them. This is the proposed overall architecture for category-level object pose refinement. Following prior methods, we use the initial estimation to transform the shape prior. Then we apply our proposed feature extractor to both the target object and the transformed shape prior for feature extraction. The HS feature extractor captures local and global geometric information using a graph convolutional layer and aligns geometric features with learnable affine transformations. We then introduce a novel cross-cloud transformation strategy, which mixes information from the two inputs, allowing the neural network to better understand the pose difference between them. After obtaining the global information, we leverage both the feature of the target object and the shape prior to accurately estimate the relative pose and size. We conducted extensive experiments to validate our method. In ablation studies, we confirmed the effectiveness of each proposed strategy. Incorporating shape prior information in pose estimation branches increased baseline performance by 2.4% on the 10 degree 2 centimeter metric. Using the HS feature extractor significantly boosted performance, with several metrics improving by over 6%. The cross-cloud transformation further enhanced our model, with the highest improvement reaching 10.5%. Our experiments also demonstrated robustness to different shape priors. Instead of only using the mean shape of the category, we randomly sampled two models from the training set and used them as shape priors. In the bar graph, the blue bars represent the baseline's results and the pink bars represent our results. Compared to the baseline method, our approach maintained stable performance, while the baseline method's performance dropped significantly when not using the mean shape as the prior. We also tested our method's robustness to different initial estimations. In the line graph, solid lines represent our results. The dashed lines represent the baseline's results, showing performance changes after each refinement iteration. The performance at iteration 0 represents the accuracy of the initial pose estimations. As seen, while the baseline failed to refine some initial poses, our method consistently improved them. For category-level methods in real-world applications, a key characteristic is their generalizability to larger unseen sets of items and objects. To evaluate this, we trained our approach using only 2% of the training set. Remarkably, with just 5,000 images, our method outperformed the baseline, which was trained on the full training set of 275,000 images. We believe this demonstrated the generalizability of our method. Our refinement results show substantial improvements in initial pose estimations, with the highest improvement being 39.1%. Even with a weak initial pose estimator, our refinement outperformed the state-of-the-art pose estimators. On the Camera 25 dataset, we observed similar results, significantly improving initial pose estimation and outperforming state-of-the-art methods with just 2% of the training dataset. Here are some qualitative comparisons between our method and the baseline. The ground truth is shown in white lines, the baseline is in blue lines, and our method is in green. Note that for symmetric objects, the estimated rotation is considered correct if the symmetric axis is aligned. As you can see, our method performs better, especially for complex-shaped objects and even when part of the object is occluded. For more details, please visit our project page. You can also find more of my work on my personal page if you are interested. Thank you.